S1, he fork T1, and then he tried to join on S1. And when he tried to join on S1, this is where the main thread gets stuck. Okay. Now let me show you what happens when I have a worker. Now the worker doesn't get stuck. Okay. Now let's see what happens. Now the first exec the first task, the same as main, fork S0, same as main, fork T1, same as main, then join on S, S1 join. When S1 join, you see that something different is going on now. Okay, something different is going on now. So when this worker thread join, right, it actually executes S1. When you join on S1, it executes S1. Okay. So this is the difference. This is the key thing that I discovered by doing this. Now, let me trace through what happened in terms of the workers queue. Okay. So this is the same output as before. So I exec the first pass, I fork S1. So after I fork S1, what happened? Right? So S1 gets into the back, right? And then I fork T1. Right? Fork T1. So T1 gets fork entered the back. And then I join S1. Now this means this worker 3 here is now waiting on S1 to complete. Okay? I'm waiting for S1 to complete. Now what happened to W3? W3 was waiting for S1 to complete. We found that it actually goes and executes S1. Not T1, execute S1. So while you wait for S1, he basically executes this task of it. Okay, so this is what this trace is telling us. By executing S1, he will fork S2, right? He will fork S2, he will fork T2, and then he will wait for T2 to join, right? Wait for T2 to join. And then when you wait for T2 to join, what does it do? It executes S2. Okay. So this is the different behavior from what I told you. Okay. So while it's true that while it's waiting to join something, it does not sit there idle, but it actually does more than that. It actually executes the task that it is joining on, if that task is still available. Okay. Now, if you think about this, intuitively it actually makes a lot of sense, right? So I ask somebody to do the task, and I'm waiting for that task to complete, and nobody else is doing that. Then I might as well just do that task myself, take it back myself and do it, right? So that I don't keep waiting on that forever, right? So this is what we are seeing here. When you join for a particular task, right, you see that S1, when you join on this task, you actually execute that task if it's available. When you join on S2, you actually execute that task if it's available. So that's why when I have only one worker thread, right, it does not get stuck. Okay. Now, for the main thread, it actually behaves differently. And I have no idea why it behaves like this, but when it joins for a task, right, it doesn't pick up that task to work on, unless it's the task at the head of the queue. Okay. Which is like question one. Question one, you do T1 join, and then T1 is the only task at the head of the queue, you pick up T1. Okay. So this is something that we discovered. So just as a reminder, all these are not documented in the fork join pool documentation. So if you go and read, you look at the description for join, it doesn't say what happened when the task is trying to join. It just says wait for the task to complete. Right? Now, all these things is not documented, so this means that it can change in the future. Right? So this is Java JDK 11. This is the behavior now. In the future, the behavior might change. They might change how fork and join works. Okay? But this is just for your info about how fork and join actually works and why is it that sometimes you get stuck, sometimes you don't get stuck. Okay? But the safest thing is still to do fork and join in the reverse order. Right? So you fork, and then when you join back in the reverse order of the fork. So that's the safest. Okay? Because that will never get stuck whether it's a main or whether it's a worker thread. Is this clear? So this is what I want to clarify about your question 1 from the last problem set. Okay. Now you can go back and you can do something like what I did here, just print out a lot of if then else, print out a lot of labels about what is being called and so on, and then you can go back and trace to understand the behavior of the program, right, if you wish to. Okay. If there are no questions, then I'll move on to the new problem set number 10, which is on only one class, the computable future class. And this is kind of an important class because it allows you to do things in a completely different way than what we are used to, right? So 2030, we keep showing you new ways of writing programs, right? Instead of just writing, imperatively from one function to another, we show you can use OOP, right? While the behavior of your program can change depending on how people inherit your class. I'll show you the creative way where you just use strings. You write what to do instead of how to do it. We'll show you fork join pool to compute recursive class parallelly. And then this one is about doing the task asynchronously. So we have explained to you what is asynchronous. We are explained to you about future and computable future during the lecture. But we did not have time to go through the APIs provided by the computable future. So this exercise is mainly for that, right? To make you go and read the documentation to try out all these functions, right? And we pick five or six methods that will be useful for your upcoming lab. Okay? So this is what the question is about. You are given the class A, and this A is a very simple class. It has a counter X, and then you just increment and decrement X. But we pretend that this is a very slow operation, right? So we do a sleep, right? Every increment and every decrement take 1 second to complete. Okay? So to increment, I sleep first, and then I add 1. To decrement, I sleep first, and then I minus 1. Right? By the way, decrement also throw an exception when the value dips below 0. Okay? So this is the class A. And these are the methods that we try to make you run. So in question 1A, you are told that there's this function foo, takes in an A, and then just do something useless. Just increment A, decrement A, and then return the value. Okay? But this operation will take 2 seconds. Okay? Now to show this to you, I'm going to call foo with a new A, and then I'm going to print down. Java. Okay, I'm going to compile and print and say 1, 2 seconds. Okay, 1 second, 2 seconds. Okay, so this thing takes 2 seconds. So in this question, we want you to modify foo so that it executes asynchronously, and it returns a computable future, right? So this thing we need to return a computable future, right? And now I need to return a computable future that execute this thing, execute A increment decrement. Okay? Now the part A actually asks us to do it in 3 different ways. One is to use supply async only. Okay? So let's see what is supply async. Supply async. So supply async basically takes in a supplier. It returns new computable feature that asynchronously complete a task running in the software tool with the value obtained by calling the given supplier. Okay. So we're going to pass in a supplier. So what we do is we just wrap supply async, wrap this call in a supplier. And this is what you have been doing for your infinite list many times. Okay? So now let me run the program, compile and run, and boom. Okay? So now you see that I asked the computer future to run the increment, decrement, the 2 seconds operation asynchronously, right? So and then I just print out that. Right? So it takes almost no time at all for my done to be printed. Now the only thing missing here is that I did not wait for the asynchronous task to be complete and return. Okay? So let me now do that. So I can do I join here, right? But if I do join here, there's no point calling my task asynchronously. So you can see if I create a computable future and immediately join, it still takes 2 seconds before I print out my done. Okay. So it's like I just call somebody to do something for me and then I just sit there and wait. I'm not doing anything useful. Okay. So instead of calling join here, what I should do is I should store this in somewhere, computable future equals to this, and then I do cf of join. So while the task is running, I'm printing up my done message, and then I wait for the asynchronous task to complete after 2 seconds. Okay. You see the difference? I print out done first, right, and then while my task is running, I print out the who is working on the task and the ID. So this is how we use supply async. The question asks us to also try using supply async and then apply. So the code will look something like this, right? So then apply is very similar to your map method in the optional, in your trace, in your lazy, in all the things that you have seen before, right? So we basically take in a function and then apply this function to the value inside this class, right? So I can do supply async increment. After increment will return me a computable future with a certain A inside, and then I apply this method to decrement it again. Right? So instead of doing it one step, A increment, decrement, I just split it into 2 steps. First step, create computable future to increment first. And then I create another computable future to decrement it. Okay, so this is using then apply. Now, you might think that the code earlier works perfectly fine, right? So I can do that increment, decrement like this. This is perfectly fine. So why do we need to do it with then apply? So what's the use of then apply? In fact, everything that you want to do, you can just wrap a supplier in it and then put the supplier sync. Now, then apply is useful in the case where you are not the one that creates the computable future. Okay? So here you create the computable future yourself, so you can lump everything together into one. But let's say that the computable future is given to you by another class, another method. Right? Let's say I do foo new A. So foo gives you a computable future. Then what you do is you want to do something to this A, then you do then apply. Right? Something like this. Okay? So then apply is useful in this context. Okay? Now what happened with the third one? The third one is then apply sync. Okay? Now let me revert back to then apply first. And then I want you to spot the difference with then apply and then apply sync. Okay, let me remove this first. Okay. So this is then apply. Right. I run one more time, then apply. Okay. And then I do then apply a sync. Okay. Do you see the difference? Okay. The difference is that if you do just then apply, it is worked on by the same worker. It's always worker 3. If I do then apply a sync, then apply a sync means that these new things that I ask my computable future to complete is run asynchronously as well. So this means that I create another thread to work on this task. Okay? So here I have 3051, 3051, right? So worker 3, worker 5, worker 3, worker 5. So they are worked on by different workers. Now, in the previous session, there was a student that asked, what's the point of doing then apply a sync? Because you, even though you spawn off another thread to work on, this other thread cannot start until your thread, your previous one completes, right? So it still takes 2 seconds. Correct? Right? This thing still takes 2 seconds. Even though it works by different tasks, the next task has to wait for the previous one to complete. So in this example that I gave, there is no difference in terms of execution time, whether I use then apply or then apply a sync or not. Okay. So let me revert back to this, to just using supply a sync, and then I'm going to show you an example where it makes a difference. Okay. So now suppose I do supply a sync, right? I do supply a sync here, increment, decrement. So this takes 2 seconds already, right? And then I do I take the A that I return from foo, and then I do increment one more time, right? And then I take the same A returned by foo, and then I do another operation. Okay. So let me CF. Okay. So I have now the first computable future returned by foo. Then I take this computable future, I apply increment one more time. Take the same computable future returned by foo, increment it one more time. Okay? So, and then after that, I join 1 and join 2. So let's see how long it takes. 1, 2, 3, 4. 4 seconds. Right? We look at the last two lines. 1, 2, 3, 4. Okay? The last two numbers appears one after another afterwards. Right? So, because the last two is still worked on by the same thread. Okay? So you still see worker 3 doing the same work. Now, then apply a sync make a difference here. So if I do then apply a sync, okay, if I do then apply a sync, then let's see what happens. 1, 2, 3, 4. Oh, it's still done by worker 3. Okay, let me make it more explicit. With 2, apply a sync. Okay, so you see 1, 2, 3. Okay, one more time. 1, 2, 3. Right, you see the last two appears together. Okay, and because they are worked on by different workers now. Okay. So if you have some tasks that you want to split off, do more synchronous, add more parallelism from the one source of information, then you can do then apply a sync 2 times. Right. Then these 2 tasks will be operated on asynchronously. So that's about supply a sync, then apply, and then apply a sync. Now, at every question at the end, we will also ask you to look at other APIs. We don't have time to go through everything, but there are certain things that are useful for you, like then run, then accept, run the sync as well. Right? So you should go and take a look. Okay, now move on to part question 1b. 1b, we are asked to make this method bar asynchronous as well. So I'm just going to copy this one over and just change the name to bar. Okay, so nothing fancy here. But the more fancy part is what happens if you want to join, compose these 2 functions together. Right? Suppose I want to compose 2 functions, like bar and foo. Normally we do f and g, right? So here's the same thing. We want to do bar and foo, compose them together. Run foo first, followed by bar. Okay. Now, I cannot do bar foo like this now because foo now returns a computable future, whereas bar takes in an A. Right, so the type doesn't match. Okay. So the question asks us to look at the then compose function. So let's look at that. What is then compose? So then compose, return a new completion state, which is a computable future that's computed with the same value as the completion state returned by the given function. Okay. And when the state completes, normally given function is invoked. So it sounds just like map. In fact, let's skip all of that and then just look at this line. So you see this method is the same as flat map. Right. So it's the same as flat map in optional, the same as flat map in your lazy, the same as flat map in your trace, etc., etc. Okay. So we all know how to use flat map, right? So I do my foo first. So this gives me a computable future. And then I'm going to do a flat map, or actually I do my then compose with a function. And what is this function that I want to call? I want to call bar. Right? And you see bar returns a computable future. Right? So the type actually matches. So I take in a function that takes in A and then return a computable future of A. So this line here is what is equivalent to doing bar.foo. on mu A. Okay. So then compose is like our flat map. Moving on, let's look at bars. Okay, again, I'm going to change this from returning A to returning a completable future of A, right? And increment, decrement, I know what to do. I just copy this line over. Now, the tricky part is this line, right? Originally, we say that if x is 0, then I don't do my 2 seconds operation. I just create my A and then returns it. Now, we can do something like this, completable future, supply a sync new A. Right? So I wrap my value in the supplier. I wrap my value in the supplier and then return this supplier. Pass this supplier into supplier C. Now that's fine, but actually we are doing some extra work. So the extra work here is the following, right? So creating new A doesn't take a long time. So there's actually no need to create a completable future, start a new track, then create, run new A and return the value and so on. Okay? So we have to find a better way to do this. And the question gave us a hint. The question said, look at completed future. Right, so what's completed future? Completed future basically returns a new completed future that is already completed with the given value. So completed future is basically a wrapper. I give you a value, you just wrap a completable future around it and then return that completable future. Right? It does nothing fancy. So we do completed future of new A. Okay. So this completed future, right, actually it should remind you of the OFF method. It's an optional OFF. I give you a value, you just wrap around optional around it. Or your lazy OFF, or your trace OFF, or your string OFF, right? It's the same thing, okay? Same concept. So what we want to show you for question A, question B, question C is that you have your then apply, which is similar to your map. Your then compose, which is similar to your flat map. And then you have your completed future, which is similar to your OFF. Okay? So this pattern, like with map, flat map, and OFF, actually is something that you have seen before, which is a monad and a functor. Okay? And completable future, this class itself is actually a monad and a functor. It actually obeys all the functor's law. That's why we can do composition like this, right? And you can check the associative law, left associative, right associative also follows. Okay. So completable future is the third monad you see from Java API. Okay. So you're seeing optional, you're seeing string, now you're seeing completable future, right? And you also build two of your own, right? You build trace and you build lazy, right? So remember what is monad? What we say is a monad, you have some value and then you have a box that provides some magic, right? So optional, the magic is that the value can be there, it might not be there, right? Lazy, you have a value inside the box and then this value will not be computed until you need it, right? Trace, you have this magic that you can revert back to the previous value, okay? So completable future is the same thing, is a value inside the box, and the magic that this box provides is that this value might not be available now, but it will be provided to you sometime in the future, right? So that's the context, the magic that this monad provides for us for computable future. Okay, so that's what we want to tell you for question A, B, and C. Now for part D, we are going to do something that is useful for your lab, upcoming lab. So I have, let's say I call my full bar and bus. Right? So this creates 3 computable features. Now the question wants us to print out done when all 3 of these methods call complete. Right? Okay. Now, one thing you can do is you can do join. Right? You wait for first one to complete, then you call the second one, and then you wait the second one to complete, call the third one, and so on. Right? So if you do something like this, you guarantee that done will be printed after the first 3 are completed. But again, I told you that we shouldn't do join so easily. We should join in the last minute so that every task that we launch asynchronously will take advantage of the parallelism. Okay? So we shouldn't do join like this. What we are going to do is to use a method called all off. Okay? So this is what the quenchers has hinted to us. So let's check out the API. What is the API? All off. There we go. Okay. So it returns a computable future that is completed when all the given computable future complete. Okay. So it takes in variable number of arguments, taking variable number of computable future. Now what is interesting about this all off is that it returns a computable future of void, meaning a computable future of nothing. Okay. So with this computable future of all, you cannot get any value out. And it takes in the computable future of question mark. Now recall back to your lecture about generics. Question mark is actually wildcard of anything. Okay? So computable future of question mark means that it can take in computable future of any type. Right? And you can actually mix different types. You can pass in computable future of customer, computable future of lazy, computable future of string, etc., into this class. Right? And it will create a new one that is completed when everything that you pass in is completed. So what we can do now is to say computable future of void or is computable future all of CF1, CF2, CF3. Okay. Now, at this point, I can do all dot join, in which case I wait for everything to complete, right? And then do nothing else, or you can continue to do your things. Right? So I can do then apply, or then run this. Okay. So this means that now I wait for everything to complete. CR1, CR2, CR3 completes, and then I run my thing. Or you can now start another chain. You do then apply, then consume, blah, blah, blah. Right? You can start another chain. Right? But here what we want is that I want to join everything back and then just do system.out.println down. Okay. So let me run this to show you. you see how long it takes? It takes 2 seconds. Because now I have 3 things that are parallel. Right? Each one takes 2 seconds. So 1, 2. The first 3 sort of printed at the same time, next 3 printed at the same time. Because there are three workers that are working on that. Okay. So this is about all of which you will use in the upcoming lab. Now the last part that I want to mention is about exception for question E. Now if you think about handling exception, it's a bit tricky when it comes to asynchronous calls, right? When we talk about threads, when we talk about throwing exception, right? We said you throw exception, then you go up your stack, find out which one on your stack is catching that exception, right? Then you throw that exception there for catch. When you have multiple threads, the picture is not so clear anymore, right? Because every thread is running things independently, so every thread has their own stack. So now when somebody throws an exception in another thread, how can you catch this in somewhere else? In one thread, how do you catch the exception in another thread? So it becomes a bit messy to think about. Now the other thing that we don't like about exceptions is that in functional programming we like to chain things up, right? You like everything in one statement, dot something, dot something, dot something, dot something, right? Now if you try to throw exceptions, then your code will become much messier, especially you want to throw and then catch and then continue to do something. Okay? So luckily computable future has provided us with some mechanism to catch the exception. Okay? So let me simplify this to just using foo. Okay? And remember that my class A will throw an exception when I decrement it below 0. Right? If x falls below 0, I will throw an exception. Okay? So to trigger that, I will change my foo so that it decrement A 2 times. Okay? And so I have a computable future foo. Okay? And what I'm going to do is I'm going to do then, okay, I'm going to do apply, okay, I'm going to call handle. Okay, this is what is hinted by the question. So I'm going to call handle. So let's visit the Java doc to see what handle does. Completion stage handle. Okay, so handle takes in a by function. So what's a by function? By function is just like a function except it takes in 2 arguments. Okay, so what's the first argument? First argument is a t, right? Second argument is a throwable. Throwable is something you can throw, like exception, and then it returns another type u. Okay? But in this case, I want my type to be the same. So basically, I take in A and an exception. So it takes in some result and exception, and then I'm going to return something. So maybe I return my result. Okay. So this would be how I can handle the exception. Now, handle also return a completion state, which is a computable feature. So this means that after handling the exception, I can continue my chain of things. I can do then apply, blah blah blah, and then compose, blah blah blah, and so on and so on. So I can continue my chain of stuff. Okay? But I just have some method in the middle of the chain to capture and handle my exception. Okay? Now, my code here doesn't actually handle exception because I ignore exception and just return the result. Okay? So to do this properly, we have to understand what is essentially being returned, being passed into the handle. Okay. So you look at the handle.